No, it's supposed to be on.
Okay.
How is it? Actually, I don't. Okay, so I'm Mark Boren. So I'm gonna talk about universal graphs between strong limit singulars and their powers.
The thing is, if we manage the value.
First, I would like to thank the organizers. Opportunity and great pleasure to give a talk at a conference with such a good lineup and amazing city. May I close? So I begin with stating the problem. So it's a very natural question that to ask for which cardinals does universal graph exist, meaning that that each graph on the same cardinality can be embedded as of course an induced subgraph, not more apart from the theoretic, not sure interesting question. So I start with what had been known earlier. So very easy sense of this question is for Aleph 0, it, for example, the random graph suffices. very easy. Now, also, if you are a CH, then one can easily construct a universal graph at Aleph1. So you construct an Aleph1 saturated graph, and that will work. And still the same phenomenon that one can construct a graph on 2 to the kappa for arbitrary cardinal kappa, which can embed every graph on kappa plus. And same elementary argument, there is an universal graph for strong limit lambdas. So if under nice or trivial cardinal arithmetic assumptions, not much to say. And but even at Aleph1, adding just Aleph2 many layers ruin this. Still not difficult. So that in this model there is no one. But then Sherlock showed that consistently there is a universal graph at Aleph1 with structure continuity. Okay. Oh, it's just a reference for a paper of Kojman and Sherlock, but that I would say it's rather folklore. Just say some. And also in a later version of that paper, Sherlock showed that for each pairs of regular cardinals, it's possible to force without collapsing any cardinals universal graph at the bigger the lambda cardinal and blow up the power. So can turn to a case of situation between strong limit singular powers. Assuming a kappa plus 2 hypermeasurable by sort of side. There is a model where SCH pairs at kappa. No universal graph at kappa plus. Even with slightly stronger assumption, it showed that one needs 2 to the kappa graphs on kappa plus 2. Want to have a universal collection. The first partial result on positive result on this problem was by Vina-Zamonia and Sherlock. They showed that consistently, starting from consistently, there is a strong limit singular cardinal mu with cofinality, with countable cofinality. And, 2 to the mu is larger than mu plus plus, but at least less than 2 to the mu. Just mu plus plus graphs can serve as a universal collection for graphs plus. later slide I introduced a new notation for that. 'Assertion. 10 years later, following 5 James Cummings, Magidor Morgan, prove this. Basically, this result for arbitrary finality below kappa. Later, Cummings, Simonian, Charles Morgan showed that this constellation is, assuming the supercompact, this constellation is consistent for more strongly singular Aleph omega. And later, Jacob Davis proved this for arbitrary finality below kappa. So one can force to hold that Aleph sigma. Recently, with Sharp, we have proven that assuming that the supercompact and the age whenever a regular cardinal sigma smaller than kappa is given, there is a forcing extension of the universe where kappa is a strongly singular finite sigma, where the SEH fails. So 2 to the kappa will be bigger than lambda, and I apologize for typo at the first possible place. So we are given the regular cardinal sigma below kappa, another regular lambda above kappa, and there is a universal graph of cardinality lambda. Only plus, no plus, and lambda was regular. I say a few words about the proof. The proof basically can be split into lemmas. Of course, for simplicity, we will just assume that sigma is Aleph 0. For this, we introduce the class of kappa edge-colored graphs. So instead of simple graphs, we need to work with objects where for any lambda regular, there is a forcing extension. kappa edge-colored graphs. There is another notation for the members of this class power mu for cardinal mu. So the two main lemma says that kappa and lambda are theorem. We have a cardinal chi above lambda, cofinality bigger than lambda. So we say so kappa to the lambda is chi to the lambda is chi. Then there is this forcing extension p prime, preserving cofinality is bigger or equal than kappa, which 2 to the kappa is equals to chi. Kappa is still measurable, and there exists a normal kappa complete measure which is closed under pseudo intersection of lambda many sets. And there exists universal model in that class. So there exists a kappa edge-colored graph vertex at lambda, but every kappa edge-colored graph same size lambda. Second lemma states that if they are given the ground model from starting from the model given by the first lemma, then just Frick forcing does what we want to achieve. Sorry. The second one. With the second point. Oh yeah. The main point, the main difficulty was in this point number 3. So basically, the heavy job is done in the first was done in the first lemma. Which we were proving something stronger, but for regular kappa. The second one. Second one is a bit more general than that. Work for. There's a version for Magidor and reinforcing, and I still a work in progress, but I believe that teaching we can achieve consistency for small singulars. I proved the second lemma. So we have this normal ultrafilter with close enough, being close enough with respect to the more than kappa. So assuming we have a name for the truth value, applying the Prickler lemma for every possible finite sequence can find a big set from the ultrafilter, but that finite set always decides, and this finite set comes from kappa not. Using Prickler lemma, excessively using Prickler lemma and normality. This implies that if we have a name that's from the lemma, we are given the big set A, then there exists a system of functions still in the ground model that whenever we are considering a condition with the test from the ultrafilter being in A except the ordinal delta, the value of the name only depends on the generic sequence up to delta. Okay, and so for lambda many names, we are given lambda many names, then we can apply the lemma and take to the intersection of those sets. Then here's a condition. Actually, here's a condition forcing that each tau I depends on function gi up to delta I. For the whole collection of names, can read out of the values from some initial segment of the generic. So here, working in the ground model, we can observe that the possible functions pairs f delta is a set of power kappa, and we have just for an arbitrary p-name for a graph on lambda, have just derived a graph on lambda with edges labeled by this space of functions. There is by our assumptions, there is a universal model, and we can embed this derived graph with embedding iota from our ground model, and so this function from the ground model, we prove that our graph embeds the graph naturally arising from the universal graph. There. Is there any question? So, by our assumption, there is a universal graph, universal kappa H-colored graph, and we were defining a graph. The edge is labeled by values from this function defined on finite sequence of delta with value 0, 1. The point is that this collection of functions is of size kappa. So there is a universal object. The models where instead of kappa, we color the edges by this element of the so the derived graph in the ground model embeds into universal, and from this universal graph we can naturally define a graph in the forcing extension. There is time for composition of four different forcings, and the main challenge was forcing this universal object. Done by smaller than kappa approximations. The object is just a random graph. Then later steps, we force the embedding more than kappa approximations, and only the keys we only embed into some suitable stationary set. There is no time to go into details. So that's the delicate point. Just for
Hello?